Political cartoon or whatever you want to call it.
Oh, I know. I love the cartoons. All right, so let's get into chapter 9 here. Yeah, you know, and I don't know exactly why this is. I mean, I'm sure there's counterexamples, but usually technologies come in some kind of pair or chicken and egg problem. I know we talked a little bit about, and we'll talk about it more, this Gordon Butte pump storage. You know, somebody wants to put in some wind, but you can't put in the wind because there's not enough electricity. So before you can build the wind, you got to build the dam. You know, the pump storage dam. And I think what this cartoon is depicting is that well, if you want to make electricity, you've got to get a magnet spinning, and to spin a magnet, you need some kind of turbine. We've talked a little bit about turbines in here so far for transportation. So, you know, to do that, you heat up the water, it starts to boil. Well, where does that heat come from? Well, it comes from coal in this case. So that's what they're showing here. Storage of force. That's kind of interesting. I guess that's one way to think of it. Electricity. Being born. I guess that's what that little baby is.
Yeah, basically they're just trying to, you know, steam and coal are kind of top dog, you know, when electricity grows up, is going to take over, I guess.
Oh, well, not really. I mean, the electricity is really the child. I'm not sure why they've got two men there. I mean, maybe one of them should have been a female if they're going to have the baby, but I don't know. Unless that's a woman there on the left. I don't know.
So they're both kings?
Both kings, yeah. And, you know, as we've seen, you know, much of this technology was developed in England. And, you know, one really, I think could make a pretty strong argument that the British Empire, if you will, sort of owed its success to its country's harnessing of energy and the deployment of the technology in order to move ships around the country, get the lights going on, increase the amount of manufacturing, what have you. And then, gosh, how much easier to pump electricity to someone's house than, you know, say pump heat there or pump water there. You know, just send the electricity out over wire and let it be the conduit.
Trying to pump heat would be a losing proposition.
Well, yes and no. There are a lot of really good examples of district heating in Europe. They've been able to make use of so-called waste heat. I mean, just think right now. I mean, what if there were a coal-fired power plant sitting right here in Missoula? It could just send all of the exhaust through the sewer lines, you know, right up to your house. Obviously, you wouldn't want the gases themselves, but those nice hot lines sitting next to your water lines would go a long way in saving you from having to burn natural gas at your house to make heat, or just let it warm the house. So, and well, obviously there's some engineering and some scale involved, but. Okay, so Sir Humphrey Davy, we're still back in England here, early pioneer of electric batteries, arc lighting, electrolysis. So, in the case of this previous figure, the only chemistry going on per se is the combustion, similar to what we just looked at for methane. In the case of the battery, you're looking at electrolysis, so individual electrons moving back and forth between elements on the anode and the cathode. I'm just going to read this little second paragraph. It says, adventurers explored the electrical and chemical properties of a wide range of materials during the 19th century, giving rise to a number of designs of non-rechargeable batteries or primary cells. So, you've all had your alkaline batteries and your flashlights, and that's a pretty good example. It says others were investing in the possibility of secondary cells. Those are rechargeable. And, and your lead acid batteries are that. A lot of nickel NiCad are that way, as are the lithium ions. Okay, so now we move from England to France. André Marie Ampère. There actually is a fun little Ampère museum in Paris. It was closed the last time I was there, but might be fun to check out sometime. What's mentioned here is the electromagnet. So the electrical force and the magnetic force are intimately entwined with each other. We can explore that here in a little bit with Maxwell's equations. It also says by the end of 1830, Faraday had produced the first dynamo, device capable of generating a continuous flow of direct current rather than alternating current. So he's got a rectifier in there that's making just straight DC. Okay. Now, this is where it starts to get a little bit interesting. In this magnet, and let me just take a little bit of time to show you what the shapes of the magnetic fields are. Because we always think of the electric field and the magnetic field as being perpendicular, and they are, but in kind of a special way. So I know there's going to be a kind of a cool image out here. Let me find one that's. And these are 3D. Not always easy to find the best. Let's look at it this way. Earth's magnetic field. Take an image. This one's not. Go to the kids page. This one's actually not too bad. I mean, more or less what we're looking at here is a giant donut. And so any magnetic field line that emanates from the top, out the north, ultimately comes back to the south. What's infinitely fascinating, so if you're having trouble sleeping at night, you might try to think about, well, where's the field line that's coming out of the North Pole go? Got to go somewhere. And, when you start digging deeply enough into physics, and realizing that, at some point way, way back when everything was much, much closer together, it could be that some of these field lines are still remnants of a time when the universe was much smaller and things really were a lot closer together. So I don't want to get too far down that rabbit hole, but the point is magnetic fields are toroidal. They're like big giant donuts. So now we've got the 3D image of it. Let's go here. And Maxwell's equations in Wikipedia are actually quite good. So what we're now looking at is just a slice of that donut. So somewhere in here, somewhere right along this line is that one magical magnetic field line that points all the way to infinity north and all the way to negative infinity in the south. But each one of these other little curves are just little mini donuts around that. The X's and the O's are the electric field lines. Now, if I try to draw this, what I'm going to show you is that, well, and I'll just draw one big field line over here and another one over here. So a direction that is perpendicular to these circles, no matter where I am, is just going to go right into the page, right? Because right here, the line's going up. Over here, it's going to the right. Over here, it's going down. Over here, it's going left. So, nicely, conveniently, a direction that goes into the page is perpendicular, and so is a direction that comes out of the page. So one goes in, one goes out, and it's basically a circle that's perpendicular to a donut. And it took physicists a long time to figure this out, but if we go back to Maxwell's equations, and really what Maxwell was able to do was to, let me make this a little bit smaller. And we don't need to get into the calculus, but I do want to show you that each one of these equations has something to do with who we've just been speaking about. So we talked a little bit about Faraday. This little cross right here just more or less means perpendicular to. It's sort of a special way of multiplying things together. So since the fields themselves are actually vectors, it's like the gravitational field of the Earth's surface, points towards the Earth, it's a vector. You need special vector notation to denote that. So here's your magnetic field, B, and when you see the big B with the bold, it doesn't just mean like a weight or a mass or a temperature. It's actually saying the shape of the field. That's what the thing means, and so that's why it's got the bold. Same thing with the electric field, and this cross here just means that as the electric field is changing through space, the magnetic field is changing in time, which actually brings us right back to this figure. So, as I crank my little armature, there's no current while this thing is just sort of sitting there doing nothing, right? So you can see that this circle, like I just said, the circular magnetic field is perpendicular to the donut-shaped magnetic field. I mean, it's there. I mean, it's sort of, it's pointing, straight through here, and then it's, sort of donut is swerving off into space. But as I crank that, the electric field, or the direction, is changing in time, or is changing in space, as the magnetic field changes in time. And so as you crank it, what comes out, what ends up coming out, is this sort of sinusoidal wave. And there's your AC. So every single outlet that we have in this room, across the street, room at home, is more or less the result of this happening on a big scale inside either a coal-fired power plant or a wind turbine plant. If it's solar, you've got to do some inversion on it, etc. But that's the nature of AC current. And then these two wires are here basically just to act as conductors from the plus and minus of the electric. Okay. Now, electricity can also be used for the conveyance of information. In fact, our brains and bodies use it too. I mean, our nervous system sends chemoelectrical pulses so that we can stay coordinated. And there's something in here that talks a little bit about the fact that there was I like this story. It says, a switch can open or close a circuit formed by a battery and some wires, et cetera, et cetera. Figure 9.5, which we're looking at right now, used a set of 5 needles to spell out the letters of the alphabet. So sort of very early LCD display, if you will. First tried out in 1837. Its fame was assured after the police used it to telegraph ahead and arrest a suspected murderer seen boarding a London train. in 1842. Telegraph soon became the key to efficient scheduling and organization of the railways. So again, like I said before, a lot of chicken and egg going on, with these technologies. So the police and the telegraph were making use of electricity. Another pretty impressive one says, next major step was laying of a telegraph cable on the floor of the Atlantic Ocean to join the U.S. and Europe. Laid in 1858 failed, but another one in 1865. Finally, 1866, and retrieved. So we went from 11 days of the fastest crossing for a message to just, a matter of seconds. Talks a little bit about the phone. One thing to keep in mind here is the very fundamental difference between how electricity is used. One is for control and for transmission of information, and the other one's for power. So think of like the computer inside your car versus the starter motor, or same thing in your computer. One's running the transistors, the other one's spinning the hard drive and the fan, for example. So it's another fundamental difference between how electricity is used in different
So they just put a
technologies.
big spool on the back of a boat, drove across the Atlantic Ocean.
Yeah.
And just let it fall wherever. That's insane.
I know.
I'd never thought about how they did that before.
Yeah, there was a documentary on not too long ago. On some of the optic fibers that's laid now, and much faster rate of communication, not just some little copper wire. And watching some of the repair, like if somebody some anchor snags it or whatever, it's a pretty intense repair operation. But
I wonder how many feet of cable that took, because obviously if you're out in the middle of the ocean, you're dropping it, it's going to try and pull itself all the way to the bottom.
Yeah.
So you're going to add a lot of length.
yeah, no, it's a good engineering problem, no doubt. It's been fun to be there. So incandescent lamps, you can think of the lamp as sort of somewhere between power and information. When I think of the lamp, okay, so it takes power coming over the electric lines, but what are you using it for? Well, you're using it to, read a book or figure out where your toothbrush is or what have you. Thomas Edison, I don't know why they used this sketch instead of an actual photo. And I don't know if you guys have ever visited he's got a lab in New Jersey, there's another one in Florida I've been to a few times. There are no photographs of Edison with his family, I've come to find. There's all kinds of him hanging out with like Ford and Firestone, but the guy just lived in his lab, literally. There's a few things back and forth. You don't hear about this too much, in American textbooks, but it says 1878, the chemist Swan, we were just looking at, demonstrated an incandescent lamp. At the same time, Edison did something very similar. It says Edison then proceeded with entrepreneurial zeal to set up generating systems. He actually did something in London in 1882, etc. And then went about with a commercial operation.
They sued each other,
Oh yeah, big time.
and then they decided it's dumb, and then
Partner.
made the Edison and Swanee United Electric Light Company.
Yeah, why give all that money to the lawyers? Just partner and keep it for yourselves. It's kind of interesting, right? The first, don't light the bulb with a match. What were you gonna say about?
There was a series on History Channel, like The Men That Build America. or
Oh,
something
okay,
like that.
yeah.
They had the argument of AC versus DC.
Yep.
Deal going on.
Yeah, and as it turns out, with DC for long distance, you need big fat cables, AC with smaller voltages does not require that. Some of the very early efforts, these magnets were not very, very powerful, so they had to be big. And here's just an example, and I drew one of these a second ago, the AC wave. It also talks about in your book the fact that power is I squared R. And then box 9.2, yeah, this is a long section. In fact, I'm going to take a quick break here because there's a few other things that I really want to focus on that I know are going to be on the exam as kind of stumpers. So, yeah, it's a big one. So I'll take a break right here.